For this lesson we're going to look at Pythagoras problems in 3 dimensions, or 3D. Now, in order to solve 3D problems, it's useful to learn to draw several objects such as rectangular prisms or boxes, square-based pyramids, and other shapes as two-dimensional diagrams. So let's have a look at an example. Let's find the height of a square base pyramid which has a base edge length of 10 centimetres and a sloping edge length of 12 centimetres. We start off by drawing a horizontal line followed by another one displaced slightly. We're going to use those lines to form a parallelogram. Now we want to mark the vertex of the pyramid, or the pointy part, at the top. So we need to determine the centre of the base, and we'll put 2 diagonals in to do that. Let's now mark a point directly above the centre of that base, and from there we're going to draw in the edge lengths, the sloping edge lengths from the vertex to each corner. Now when I get to the last one, notice I'm going to make it a dotted line because that's behind, so it gives us more of a 3D feel because we can't actually see that edge. Now what we're after here is the height, so we'll mark that in from the vertex down to the centre of the base, and we're going to form a triangle here which is a right angled triangle. Now we know that in order to solve this triangle, in other words, in order to find the height of that triangle, we need the sloping edge, and we'll need half of the diagonal of the base. Let's look at a bird's eye view of that base. So we've got our edge length of 10 and 10, and we've got that diagonal that goes across. Now with that diagonal, what we want to find is half of that diagonal. So first we'll find the full diagonal, and a good idea obviously to mark in some reference points. So we'll call the base A, B, C, D, and we'll call the vertex up here V. Okay. So now using this triangle here, we've got 10 and 10 as the 2 shorter sides, and X is the longest side. So we set up Pythagoras' theorem showing the 2 short sides squared and added equaling the longest side squared. So we get 200 equals x squared, so we square root both sides to get x. The square root of 200 is 14.14. Now remember that we're interested in looking at this half diagonal here, so we're going to halve our value for x. So we halve our 14.14, so the distance from A to 0, which is the centre of our base, is going to be 7.07. And now you'll notice I've drawn a second triangle here. That triangle corresponds to this one here. So what else do we know in this diagram? Well, we do know that the sloping edge length is 12. So we mark that in, and the unknown value is the height. Now when we set up Pythagoras' theorem, notice again we have the 2 shorter sides together equaling the longest side, and then we square them all. So we get h squared plus 50 equals 144. Taking the 50 to the other side, we get h squared is 94, and we'll square root that to get 9.695 centimetres. In the next example, we're going to find the longest pencil that would fit inside the pencil box shown below. So again, we're going to draw a 3-dimensional rectangular prism or box as a 2-dimensional figure, and we're going to draw a parallelogram again. So we draw one length, horizontal length, and the same length displaced slightly. We join to form a parallelogram. And this time, because it's a box, we're now going to drop some lines from each corner. Now we'll drop the left-hand line as well and form a rectangle, and then that helps guide us with placing our other lines. So we make that last line I've just drawn, this one over here, long enough so that you can imagine that if I join it now I'm going to get another pair of parallel lines here and here. In similar fashion we'll put in the dotted lines, and the longest pencil that will fit inside will not be a diagonal along the base, so it won't just go from one base corner to the other, because we could lift that pencil up and it would fall short of the back corner. So we start from the front left corner and go to the back right corner. Now that pencil has a shadow, or forms a shadow beneath it, which is the diagonal of the base. So at this point we should label our corner points and put in the dimensions, and from a bird's eye point of view we can see our base A, B, C, D, and remember that this shadow that the pencil casts is going to be our diagonal here. So we're going to use Pythagoras' theorem using 15 squared and 7 squared as our two short sides equals x squared. Solving that, we get x as the square root of 274, which is, as the arrow suggests, this value over here. Now that we have this diagonal, we're now going to use that result to find the length of the pencil by using this height of the triangle AGC, which is 6. Now notice that that line from G to C is vertical, and although it doesn't look it on two-dimensional shape, this line from A to C is horizontal because it's sitting on the base of the box. So that means we do have a right angle between those two sides. So now we'll work on that triangle, and using some colour coding you can see can help, because we can see the pencil in purple. So we use our result from before, which is the 16.553, and the 6, which form the two short sides. So y squared will equal the 274 plus 36. So y squared is 310. We square root that and we get y as 17.61.